Now next we'll come to reversible and irreversible reaction. Reversible reaction and irreversible reaction. So first we'll say reversible reaction. A reversible reaction means a reaction which can be reversed, correct, on reversing the experimental conditions. A reaction which can be reversed on reversing the experimental conditions is known as a reversible reactions. For example, ammonium chloride on heating changes to ammonium chloride gas. Got it? It changes to ammonium chloride gas. It's a solid. On heating it changes to gas because it is a sublimable substance. That is in the forward direction. Now what it is that on heating it changes to a gas. Now on cooling, what will happen is that the ammonium chloride gas changes back to ammonium chloride solid. It changes back to ammonium chloride solid. Alright, that is on reversing the experimental conditions. On heating I have changed ammonium chloride solid to ammonium chloride gas. On cooling, ammonium chloride gas changes back to ammonium chloride solid. That is called as solidification. So on reversing the experimental conditions, I have done it. So when on reversing the experimental conditions, you get back the reactants, that is said to be as a reversible reaction, so to say. Alright, that is called as a reversible reaction. And if on reversing the experimental conditions, if you don't get back the reactant, or I can say if the reaction is carried out only in the forward direction, not in the backward direction. Alright, if the reaction is carried out only in the forward direction, not in the backward direction, it is called as an irreversible reaction. That is called as an irreversible reaction, so to say. So, a reaction in which not only the reactants react to form the products under certain conditions, a reaction in which the reactants not only react to form the products under certain conditions, but also the products reacts to form the reactants under the same conditions. The products reacts to form back the reactants under the same conditions. We can say that. That is on reversing the conditions. We can say that. Clear? Same conditions or on reversing the conditions, so to say. We can say. So that is called as a reversible reaction. So in other words, a reaction which takes place only in the not only in the forward direction but also in the backward direction under the same conditions or on reversing the conditions is called as a reversible reaction, so to say. Clear? And if a reaction that takes place only in the forward direction, alright, in the forward direction, the products do not react to form back the reactants. The product that do not react to form again back the reactants, we can say that, under the same conditions is called as an irreversible reaction. So we can say that is called as an irreversible reaction. And remember that always I say you that reversible reactions is carried out in a closed container. You can attain the equilibrium process. The reaction is said to be in equilibrium because reversible reaction always attains equilibrium. Irreversible reaction never attains equilibrium because always an irreversible reaction completes. It tends to completion, we can say that. It gets completed because it moves in the forward direction. For example, you are heating something. Like suppose you have taken some paper. Simple. You just take some paper and you heat it. Alright. So you take a matchstick and you light it. What will happen? The paper is going to burn. So that is in the forward direction. We can say that. Can it attain equilibrium? No, not at all. So it is not possible. So when a reaction is carried out only in the forward direction, that is called as an irreversible reaction. That is known as an irreversible reaction, so to say. Alright, so an irreversible reaction always is carried out in the forward direction, but a reversible reaction can be carried out both in the forward as well as in the backward direction under the same conditions or on reversing the experimental conditions, so to say. Got it? So in this way, what you find is that always a reversible reactions, as I said you earlier also, that we never know that the product is gaseous or not. So if you do not know whether the product is gaseous or not, so it is better to always carry out in a closed vessel, in a closed container. Then only the equilibrium can be attained. Then only the reversible reaction can attain equilibrium. Mind it, one more thing also. An irreversible reaction never attains equilibrium. Always a reversible reaction only attains equilibrium under a given set of conditions. Got it? Clear? Fine. Now let us take an example here. What we will do is that we will take that is iron. This is a combustion tube. I have taken some iron. That is iron wool, rather we say is that Fe. I have taken it. Now I will pass steam through it. Steam. So Fe reacts with steam to form what? It forms Fe3O4 plus H2. So 3Fe plus 4H2O will give you Fe3O4 plus 4H2. We can say that. So in this way, we get a particular reactions. From here, if you pass steam through it, now hydrogen gas is released from here. Hydrogen gas is released out. Alright, so here what you are doing is that you have taken some pieces of iron. Of course, you will be heating from here. Of course, the heat has to be passed from here. So what you will find is that it forms Fe3O4 and H2. We are getting it. Fine, clear. Triferric tetroxide of iron. We are getting it. Now what you do is that now you reverse the process. What you do is you pass hydrogen gas, and here you take Fe3O4. Here you take Fe3O4. Alright, that means what I am asking you to do, I am asking you to do this particular process, that is Fe3O4 plus H2. Alright, will give you what? Fe plus H2O. Here you will be getting the steam. Here you will be getting the steam. You are passing the hydrogen gas through it. The hydrogen gas you are passing through it. Alright, so Fe3O4 plus H2. So 3Fe plus 4H2O. We can say that. Clear? Here it is 4H2. So in this way, what we find is that here we are getting the steam. In the previous case, we have taken iron, we have heated the iron wool, and we have passed steam. We got Fe3O4 and H2. We have seen it. Now in the second case, we are taking Fe3O4, reversible. Alright, Fe3O4 we are passing hydrogen, means we are reducing it. We are reducing it, Fe3O4, to what? Fe and H2O. We are getting the steam. In both the cases, the reaction is irreversible. In both the cases. But what you do is that now you carry out the reaction in a closed manner. In a closed manner, you carry out the reaction. You stop it, this particular one. You close it, this particular one. You close it. Here also, after you take a small hole, alright, you take a small hole through which you pass steam, and here you take Fe again, the first reaction I'm talking to you. Alright, you are passing steam, alright, and you have closed here. Alright, when you have closed here, what happens is that this reaction is going to take place. The above reaction is going to take place. Steam, when it's passed through heated iron, it forms Fe3O4 and H2. After some time, you will see a reaction, and this particular reaction attains equilibrium. Now it's a closed reaction. It attains equilibrium after some time. You can see it attains equilibrium. Now, after passing steam, you have to close this particular one. This, this opening, you have to close it. Now it is completely closed. This, of course, it is closed, and here also after passing steam for some time, you have to close it. Then what will happen? This reaction is going to take place, and hydrogen gas is not allowed to escape. Now you stop heating also. When you have closed this mouth, this opening, at the same time you stop heating also. When you will stop heating, listen carefully. When you will stop heating, Fe3O4 reacts with hydrogen to form again Fe plus water. You will be getting it. Fe plus water, you will be getting it. Clear? So, hence this reaction is what? It's a reversible reaction. In the previous two examples, it was not reversible. Why? Because I have kept in I have taken an open container. This was open. This was open. This was also open. It was an open container. Or it was an open combustion tube. I have taken it. So the hydrogen gas was escaping. Alright, the steam was escaping. We can say that. Clear? So hence it did not attain equilibrium. For that particular purpose, this particular one, it proves that if the same reaction is being carried out in a closed container, then only it will be attaining equilibrium, and then also it can also become reversible. We can say that. Clear? So in this way, you can attain the reversibility also. At the same time, you can attain the equilibrium also. Alright. So what you find is that when it attains equilibrium, I said you the factors. Got it? That is concentration, temperature, pressure, everything becomes constant. The observable properties becomes constant. We can say that. Clear? So this experiment clearly proves that the same reaction can be attained equilibrium if it is carried out in a closed container. But if the same reaction is carried out in an open container, then the products which are gaseous, it's allowed to escape, and hence it does not attain equilibrium. It does not become reversible. We can say that. We are not able to attain the reversibility of a particular process. So a reaction can be attained equilibrium. A reaction will be at equilibrium when it is being carried out in a closed container. We can say that. So in this way, we find it out at equilibrium, the products or the factors affecting the equilibrium becomes constant. We can say that. Clear? Fine. Now we will explain this particular thing graphically. We'll explain it graphically. Alright. So how can we explain this particular fact graphically? So for that reason I'll be taking here, that is rate, I'll be taking here. Alright. And here I'll be taking, that is time. So when you will start the reaction, alright, when you start the reaction, the concentration or the you can also take your concentration also instead of rate. The concentration also can be taken. So concentration is very high, alright, and what will happen is that as the reaction proceeds, the concentration of the reactant is decreasing. As the reaction proceeds, for example, let me give an example to you. CaCO3 solid. Upon heating, it forms CaO solid plus CO2, what you can say, gas. Always in case of equilibrium reaction, we need to mention the state of the reactants and the products. State of the reactants and the products we need to mention always. So when you are heating calcium carbonate, that is chalk or marble, it forms calcium oxide and carbon dioxide. So you can see the concentration of calcium carbonate is very high. Alright, it's maximum. When the reaction proceeds forward, the concentration of calcium carbonate decreases and the concentration of calcium oxide and carbon dioxide increases. The concentration of the reactant decreases because the reactant is used up and the product is formed. Got it? Always remember that. A reactant is used up and the product is always formed. Initially, when you start the reaction, the concentration of the reactant is high. Alright, but as the reaction proceeds forward, the concentration of the reactant is decreasing and the concentration of the product is increasing because the reactant is used up and the product is being formed. Alright, I hope it's been clear, this particular thing. Now, next is, so what you'll find is that when the reaction is proceeding in the forward direction, so this is the graph for the forward direction. You can say the concentration is decreasing. You can say the graph is moving in the forward direction. The rate is decreasing. Rate of the reactant is decreasing. This is for the reactant. We can say that. R, I am writing it. For the reactant. Now, when you start the reaction, I said you that the concentration of the product is 0. What is the rate of formation of product is 0. This is there. If the product is there, no, product is not there. Only this is there. So, you start for the product, you start the graph from in this way. So, as the concentration of the reactant is decreasing, as the rate of reactant is decreasing, reactant I am saying. So, the rate of the product is going to increase. So, at a particular point of time, when both the reactant and the product, they will meet, means when both the rate will be equal, when both the concentration will be equal. Suppose instead of rate, I said you can take concentration also. So, the same thing it is. In case of concentration, what will I say? The rate, what you can say, the concentration of the reactant is decreasing as the reaction is proceeding forward. Now, the concentration of product is increasing as the reaction is proceeding forward. Alright, the reactant is decreasing because the reactant is used up and the product is formed. So, at a particular point of time, you will find that the concentration of the reactant and the product both are same. If I take concentration here, again I am repeating. If you take rate here, what will happen is that at a particular point of time, you will find that is that the rate of the product and that is rate of the reactant and the product both the same. Alright, when the reaction attains equilibrium, it is same. Now the graph will be this sort of. So what is this point known as? This is called as the point of equilibrium. We can say that. I hope it is visible to you. It is point of equilibrium, we can say that. So, when the rate of the reactant and the rate of the product at a particular point of time, when it attains, when it becomes equal, then the reaction attains equilibrium. Got it? And this particular point is said to be as the point of equilibrium, so to say. Got it? You can do the same we can do the same graph by taking rate against time. You can also do by taking concentration against time. Just you have to change the word. When you say concentration, you say the concentration of the reactant is decreasing and the concentration of product is increasing. After a certain point of time, when both the concentration is equal, then the reaction attains equilibrium. Same thing is. You can say in terms of rate as well as in terms of concentration. You can say this as the forward direction and you can say this as the backward direction also you can say. In terms of forward direction also you can say. This is also backward direction. That also you can write it down. Let me write. Backward direction. And this is your forward direction. So you can see so many things I've said in here in one particular graph. Alright, I told you about forward, I told you about backward, I told you about reactant, I told you about product, I told you about concentration also. So the same graph can come in many different ways, but the answer is the same. We can say that. Clear? Now, in this way, you can explain this particular one. Now, I have taken an example here, calcium carbonate and calcium oxide and carbon dioxide. How can I explain it? Experimentally, this one you see. How can I explain this particular one experimentally? I think the graph you have understood. Now, for this particular purpose, you have to take a container here, which is connected to a U-tube, which is nothing but I have already said you here the U-tube means the manometer, a U-shaped tube. We can say that a U-shaped tube. This is a U-shaped tube. I have taken it. Now, in this particular one, I will be heating it this one, and here I will be taking a porcelain boat, and this boat I have taken. In this porcelain boat means the shape is in the form of boat. That is a porcelain boat. Don't think something else. So it is calcium carbonate solid. CaCO3 solid. I have taken calcium carbonate solid. Calcium carbonate is nothing but a chalk, marble, limestone, anything you have taken. Now, when you will be heating it, what will happen? Calcium oxide and carbon dioxide is being produced. So, carbon dioxide which is being produced, it goes here. Now, here what is there? That is nothing but mercury is there. Before starting the process, the mercury in both the limb will be the same. The mercury in both the limb will be the same. The mercury in both the limb. I can still lift little bit up. In both the limb it will be same. Why? Because it is at normal atmospheric pressure. In both the limb, it is at the same height. We can say normal atmospheric pressure. When you before starting the reaction. Alright, now after the reaction you have started, what will happen is that you will find that the carbon dioxide gas I have explained you earlier, this sort of experiment, one more experiment I explained you earlier. Carbon dioxide gas will push the mercury level in this limb. So this limb is going to fall and this limb is going to rise further. Got it? This is going to fall further and this is going to rise further. So when you find this is happening, you stop hitting here. You don't hit it further. Stop hitting. Now when you stop hitting, what will happen is that the reversible reaction will start. Calcium oxide now reacts with carbon dioxide to form again calcium carbonates. How do you come to know? You will find again there is a fall in the mercury level in this particular limb. It is going to fall down slowly and slowly. This process is a very slow process, mind it. It's not a fast process, very slow process, very slow. You need to have patience for this particular process. So what you will find is that it's going to fall down. Again after some time, again you will see it is going to rise a little bit. Why? Because again calcium carbonate reacts with calcium oxide, calcium carbonate which is being forming in the backward direction. Again it forms calcium oxide and carbon dioxide. Because always you know that reversible reaction is carried out in infinite number of small steps. Infinite number of small steps. A part of the reaction goes forward. Again a part of goes backward. Again a part of the reaction forward. Again a part of the reaction goes backward. In this way you will find that sometimes the level is going to rise little bit, sometimes the level is going to fall little bit. But after a particular time you will find the level becomes constant. At a particular height it becomes constant. It neither rises further nor it falls further. So what we can say? The reaction attains equilibrium at that particular point. So what is the properties which becomes constant? The pressure becomes constant. We can see it. We can observe it. Very clearly we can observe it. That the pressure becomes constant. Alright, in this way. So when a reaction attains equilibrium, one of the observable properties becomes constant, which as you can see from this particular experiment. Alright, the level of carbon, mercury in one of the limb becomes constant. Neither it falls nor it rises. Initially it falls and rises slowly and slowly it rises and falls. But after a particular point of time it becomes constant when the reaction attains equilibrium. In this way we can explain the process of equilibrium by this experiment. Here the pressure we can see it becomes constant. Now we will take another experiment. We will take that is a glass bulb. Alright, we will take a glass bulb which contains nitrous N2O4 gas. This is a glass bulb. It is in the shape of mango. We can say that. Clear. So just to explain, you have taken this N2O4 gas. Now N2O4 gas is quite stable at 0 degrees centigrade. So it is what? It is a colorless gas. This gas is colorless. N2O4 gas is colorless. Here N2O4 gas is there, which is colorless. We can say that. Clear, it is colorless, N2O4 gas, and it is quite stable at 0 degree centigrade. So at 0 degree centigrade, when you put it in ice cold water or you put it in ice, it remains colorless only. Alright, it remains colorless only, mind it. Now what you do is that you shift this. It is in, what is that? Ice cold water. Ice cold, or some ice is there in it. Some ice. This is some ice I have kept it, which is at 0 degree centigrade. Now, what you do is that you shift this particular glass bulb, you shift this glass bulb into what you can say water at room temperature. Generally room temperature is what? 25 degrees Celsius. You shift this glass bulb, got it? You shift this glass bulb. Let me make it a little bit properly. Yeah, let me make it a little bit properly. You can say this is a glass bulb. I have taken it, I have shifted it into water. This is at room temperature. Now what you will find, listen carefully, it changes from N2O4, it changes to what you can say NO2. So this colorless, now it becomes what you can say slowly and slowly reddish brown color. Got it? Slowly and slowly it changes to reddish brown color. Got it? When you shift the glass bulb from ice cold water, or ice, we can say that, and you are shifting it to what you can say in another beaker which contains water only, normal water, and the water is at room temperature, which is 25 degrees Celsius. Generally, room temperature is considered to be as 25 degrees Celsius. You will see the colorless, the gas which was colorless changes slowly to reddish brown. Slowly, the color changes. Here it becomes reddish brown in color. Initially it was colorless, it changes to now reddish brown, we can say that. Because it changes from N2O4 to NO2. Rather, I'll balance it, it becomes 2NO2. Alright, so it becomes dark reddish brown color. Followed? Now, what you do is that after some time you will find that the color is neither so dark nor so it is pale. The color becomes constant. Initially, from colorless it changes to reddish brown, dark reddish brown. Then after that you will find the dark reddish brown color slowly fades away. Got it? Got it? It slowly fades away. It becomes slowly colorless. Again, it becomes slowly little bit reddish brown. Again, it slowly fades away. Then after a particular point of time, the color becomes constant. It neither what you can changes to reddish brown further, nor it becomes to further what you can say pale color. The color becomes constant. Why? Because this reaction attains equilibrium. So when the reaction attains equilibrium, the color becomes constant. This is also another observable properties. So by this all experiment, you can say that the reaction is attained equilibrium. Very clearly you can say that the reaction is attained equilibrium. Got it? So all this experiment, reaction between H2 and I2 to form HI, that is also another experiment. We can say that, where you can show that the reaction has attained equilibrium. The reaction between ferric salt and that is thiocyanate, SCN minus salt, to form what you can say reddish brown, that is ferrous thiocyanate, we can say that. Clear? So that is also an example of an equilibrium reaction, so to say. Clear? So in this way there are many reactions. So we can have it, as I said earlier also, there are many reactions, there are many processes we can have it by which we can say that the reaction has attained equilibrium. So remember it, when a reaction attains equilibrium, the observable properties, right from the beginning I am saying that observable properties becomes constant. Got it? And observable properties becomes constant, and the reaction is always dynamic in nature. Got it? How can we explain this particular thing, that the reaction is always dynamic in nature? Now for that particular purpose, what we can do is that we can just know this particular thing, that is we will take 2 cups. Alright, 2 cups we will be taking it. Cups, you know where the hen are there. Hen. In one cup, what you can say brown chickens are there, and another cup that is white chickens are there. In between one door is there, a small door is there. Now initially in one cup, what you can say brown chickens, and another cup that is white chickens are there, kept separately. In between a door is there. When you open the door, what will happen is that the hen will move from one coop to another coop. At a particular point of time, you may find that the number of hens that is white and brown is same in both the groups. Let us say here 5 hens, white is there, 5 brown is there. Here 5 brown and 5 white is there. That means you can find the number of hens in both the coop at a particular point of time. It may happen. You can say how it can happen. It may happen at a particular point of time. That it's not that the hen are moving accordingly. That okay, 5 is there. Okay, I'll be 5 is there. No, it's not way. Unknowingly it can happen. That the number of hens, white and brown, in both the coops will remain the same. That means what? We can say that the reaction is attained equilibrium. We can say that. Clear? Now at that particular time, do you think that the hen stops moving? The chicken stops moving from one coop to another coop? No, still it moves from one coop to another coop. Even after attaining equilibrium, you can find some of the hens will be moving from white to brown, or from the brown to white it will be moving. So what does it mean? That after attaining equilibrium also the reaction is dynamic in nature. Even if it attains equilibrium, the reaction is not static. The hen does not stop moving. Hens are still moving from one coop to another coop. But at a particular point of time, you may also see that the number of hens in both the coop, got it, colored hen in both the coop remains the same. Got it. So similarly, you can also say another experiment, like let us say I have taken a vessel here. Water is falling from here, inlet, and water is coming out from here. Both the, here water is there. Alright, this is a very good experiment. Here water is there. Now, the rate at which it is filling the tank and the rate at which it is coming out of the tank, both the speed has to be the same. Means by the help of a, what you can say, tap, you are filling the tank. By the help of another tap, you are also taking out the water from the tank. Now, when both the rate are same, when both the rate are the same, you will find that the water level in the tank remains constant. It does not increase nor decrease further. The water level remains at this height only. It neither decrease further nor it increase further. You can just put a mark here. In this way, a mark you can put it and you can find it out also. When the rate of entering the water into the tank and the rate of exiting the water out of the tank, means by the tap which you are filling the water and by the tap which the water is being exited out from the tank, if both the rate are the same, both the speed are the same, the speed of water is the same, then you will find the level of water in the tank remains constant. Alright, that means the reaction is attained equilibrium. But at that particular time, have I stopped the inlet and outlet? No, still it is going on. So it proves that the reaction is also dynamic in nature. Alright, when the level becomes constant, have I stopped this particular inlet and outlet? Have I closed the, what you can say, this tap? No, still water is entering and still water is coming out. So the reaction is dynamic. The reaction is at an equilibrium, but at the same time the reaction is also dynamic in nature, because still water is falling and the water is living. It is falling and living. It is falling and living. Alright, so in this way the reaction is dynamic in nature. So all this, what you can say, experiment proves that when the reaction attains equilibrium, the reaction is never static. The reaction never stops. The reaction is always dynamic in nature. Got it? But the thing is that both the rate has to be the same, we can say. Like in this case I have said. So hence the characteristics of the chemical equilibrium. Earlier I have said you characteristics of equilibrium. Now I am saying you characteristics of chemical equilibrium. Both the same almost, we can say that. At equilibrium, the concentration of each of the reactants and products becomes constant. Yes, concentration of the reactant and product from either of the direction becomes constant. Now, at equilibrium, the rate of forward reaction becomes equal to the rate of the backward direction, and hence the reaction is dynamic in nature. The rate of the forward is equal to the rate of the backward direction. Hence, the reaction is said to be dynamic in nature. A chemical reaction can be established only if none of the products is allowed to escape, that is, or separate out. Alright, that's very important point. If none of the products is allowed to escape, that is, when the reaction is carried out in a closed container. I have said you right from the beginning. Chemical equilibrium can be attained from either of the direction. You can attain equilibrium from either of the direction. You can get equilibrium from the forward direction. You can attain equilibrium from the backward direction also. It is not necessary. The reaction is can be attaining equilibrium from the forward only always. It can be attaining equilibrium from the backward also. For example, I told you nitrous oxide and NO2. So I have started from nitrous oxide and NO2. You can start from NO2 also. You take the NO2 glass bulb which is reddish brown in color. You put it into ice cold water. It becomes what? Colorless. It becomes colorless after some time. Alright. Now what it is that you take that particular glass bulb and you put it into water, normal water. Got it? So what you will find is that it becomes same color. What the color becomes? Same. Same means neither it is dark reddish brown, neither it is pale colorless, we can say that. The color is constant. Alright, you can do two experiments in this way. One glass bulb, you can bring it from what you can say, nitrous oxide to nitrogen dioxide and put it in normal water. Another glass bulb, we can bring it from nitrogen dioxide to nitrous oxide, and both the glass bulb we put it in normal water. You will see both the glass bulb will have the same color. Have you understood what I said? That is, you have taken nitrous oxide, N2O4 to NO2. N2O4 to NO2. Now N2O4 is colorless and this is reddish brown. You take a glass bulb which contains N2O4 gas. You take a glass bulb which contains NO2 gas. Now this was at higher temperature, this is at 0 degree centigrade. Now both the glass bulb, you put it into what you can say, in a beaker which contains water at room temperature. Both the glass bulb, we put it into a beaker containing water which is at room temperature. Now N2O4, the glass bulb which contains N2O4, let us say the glass bulb A which contains N2O4 gas. It becomes what you can say reddish brown after some time. Got it? Now the glass bulb B which contains NO2, what you can say, NO2 gas, the glass bulb B which contains NO2 gas, and this is N2O4 gas. Now both the glass bulb we are putting into normal water. Now this attains equilibrium in the forward direction and this attains equilibrium in the backward direction. How do we come to know? The color in both the glass bulb becomes same. That becomes constant. Initially you will find that it changes from colorless to reddish brown, dark, and this from reddish brown it becomes colorless. But after some time, correct, as it is at the same water, at same 25 degrees Celsius, at normal temperature, we can say that the color becomes constant. So what I say, that only I am saying right from the beginning, that this is attaining equilibrium in this direction, in the forward direction, and this one is attaining equilibrium in the backward direction, because in both the cases the color in the color of the gas inside the glass bulb is the same, is constant. So this attains equilibrium in the forward direction, this attains equilibrium in the backward direction. So hence I said equilibrium can be attained from either of the direction. And a catalyst never alters the rate of, a catalyst never alters the state of equilibrium, we can say that. It never alters state of equilibrium. What it means, if a reaction is not reversible, can a catalyst make it reversible? Or if a reaction is reversible, can a catalyst make it irreversible? No, because catalyst does not alter the state of equilibrium, catalyst alters the rate of equilibrium. If you are taking a catalyst, the equilibrium will be attained at a faster rate. If you are not taking a catalyst, the equilibrium will be attained at a slower rate. That is the thing. A catalyst does not alter the state of equilibrium. A catalyst alters the rate of equilibrium. If you are taking a catalyst, the equilibrium will be attained at a faster rate. If you don't take a catalyst, the equilibrium will be attained at a slower rate. That's all. Thank you.